Stanford University.
Good afternoon. Welcome to EE 380, the Stanford EE Computer Systems Colloquium. Just to give you an idea of what's coming up, 2 weeks from today, Pam Samuelson from Berkeley and the law school is going to come and discuss the Google book case and some of the ramifications from the recent decision there. As we know, content is everything, and the Google book decision has got a lot to do about what is going to happen with content in the future. It's an issue of copyright law, but it's also an issue of what access people are able to get to materials. Next week, I'm not certain I can do this. Shuram Krishnamurthy from Brown University, who's one of the authors of Racket, is going to come and he's going to talk about reactive functional programming from models to classrooms. This is about finding the proper elements to teach about programming when you construct languages and teach people about what programs really do. Today we have an interesting sort of two-component talk. On the one side, we're going to be talking about finance and banking. And on the other side, we're going to be talking about how to build supercomputers that actually run fast. The issue here is interesting. As computation has become more of a driver in the issue of finance and banking, the expectations about what you can do and should do have grown to the point that they perhaps exceed the ability of today's general purpose computers to perform effectively. And so it's a problem to make things run fast enough to be useful. In addition to having to have a theory for how to model finance and how to understand what is observed and what impact a particular action might take, there's also the question of being able to do it in a time that's actually useful. And there, I believe, going to tell us a little bit about the mechanisms by which we can build very fast, very powerful supercomputers which can be used in practice in the financial industry. Our speakers today are Stephen Weston, who is from the London office of J.P. Morgan. He's a quant. That means he understands the issues of how you model financial risk. And our second speaker is Peter Richards, who is there from the New York office of J.P. Morgan. And his role in the world is how to find machines that will actually do what the quants need to have done. Gentlemen, please welcome Peter and Stephen. There you go, guys.
Thank you very much. Good afternoon. We're actually switching the order in which we were introduced. So I'm Peter Richards, and my job is to explain why we care about technology in the financial services industry, and in particular at JP Morgan Chase. JP Morgan Chase is a full-service bank. I probably have to do this, don't I? I can only do one thing at a time, right? So I don't multi-process. Your brain does. But it never tells me what's going on, right? So the business challenges in banking are actually ones which aren't immediately recognized as technology challenges. And from my own experience, 20 years ago when I moved into financial services, I had no desire to move to financial services because they clearly were fairly dull, right? The problems were ones of counting, pieces of money, adding them up. And the only thing that got me there was somebody offered me free lunch. And 20 years later, I'm still here. The reason I'm still here is because the challenges are actually quite fascinating. And what I want to do is spend a couple of minutes explaining some of the things which are challenges to us, which are actually technology challenges, but have real impact into our business. And then Stephen will take one of those types of challenges and explain what we've done in conjunction with Oscar and his team to actually apply some of the technologies to produce a real valuable result. So I'm going to open my notes. Did I cover that? Pretty much, right? So let's move on. We titled this Scale and Complexity, right? So I'm going to give you a few numbers about scale on the next slide. But one of the things that I want to emphasize is that whilst we may have a lot of something, we don't have the most of it, be it computers or desktops or network nodes or data center square footage, and we'll come to what the numbers are in a second, but we have a lot of complexity. We run multiple different businesses. So some of you may be Chase customers, that's part of JP Morgan Chase. Some of you may be Chase credit card and debit card holders, that's also part of us. A few of you may be private wealth customers where we help manage your money, and a few of you may be members of companies and institutions where we manage your institution's money. So that's sort of on the wholesale side of the world, and we do investment banking, and we do treasury services, and we do wealth management and asset management, and we also do corporate banking. All of these disciplines actually pose some similar and some dissimilar technology challenges. And it's that complexity and that mix of a wide variety of things which makes it very interesting to be part of the technology team within this group. So we're going to do all this, okay? And there's some Q&A, so if we miss stuff and we don't cover a point to your satisfaction, then you can ask Stephen all the questions. JP Morgan Chase.
Yes, exactly.
You've got to try and ask the question because then we'll see if we get an answer. There are some unanswerable questions, like what am I supposed to talk about next? We have 240,000 people that work at JP Morgan Chase globally. Our retail side of the business tends to be domestic US, and so that's a very large set of customers, but our wholesale side is global. So we're in 47 plus countries. Probably didn't have that. We actually have 24.5 million checking accounts, 5,500 branches, and 15,500 ATMs. However, as my daughter points out, in the college town that she's at, which happens not to be here, there are no Chase ATMs. And I've actually talked to the people who decide where our branches go, and they said, no, we have no plans to put them there. So we're not quite yet everywhere, but there's a lot of stuff.
I mean, I can't use my cell phone yet?
You can, right? And we're going to come to that, right? But you can't in the basement because we've no signal, as you know, right? We got, almost 140 million credit cards in circulation. And we actually have almost $2 trillion worth of assets under management. And we clear $5 trillion daily. What does that mean? That means that in our trading businesses, we actually transact $5 trillion worth of trades on a daily basis. And we go through and we make sure they're matched, and we clear them through clearinghouses. It's a scary number, right? There were times, and in fact, a year or so ago, there was a time where the foreign exchange rates and the trading rates spiked, and we got very, very close to actually hitting the bump stops at the clearinghouse, right? So we had the challenge of making sure we could put the trades to the clearinghouse, but the clearinghouse were, shall we say, breaking into just ever so slightly a little bit of a sweat, right? So all of this stuff helps global commerce move, right? So it's not just because we like playing trading, right? It's all got a reason, right?
With the clearing, were you hit by the Iceland issue?
When Iceland defaulted?
Yes.
A little bit, right? But that, I mean, Stephen can talk better about defaults than I can. Right? I can, no, in all seriousness, right? Because like credit and credit defaults are what Stephen does, right? I can talk about the flow of the process. So in some ways, I care less about what the trade is, just to make sure it gets to the right place, we match it, and we settle, right? So, you know, what causes it is important to us, but Stephen is in the side of the business that cares about what causes it and deals with the consequence of that.
When you use the term trillion, which trillion did you mean? It has two very different meanings.
It has?
Yeah.
See, I'm going to get educated. Fantastic.
Well, one is a 1,000 billion,
Mm-hmm.
and the other is a billion billion.
1,000 billion.
1,000 billion.
Right.
A smaller number.
If
Still a
I,
large number, but significant.
just as an aside, right, when I was growing up, a billion was actually a million to me, right? But as I grew up, I discovered that there was another country that had a different definition, right? So I don't know if a trillion is in the same ballpark.
It is in the same way.
Okay,
And we're learning to cope with finance.
okay. So just all cards on the table, right? I now live in New York City, so to me, a trillion is 1,000 million, 1,000 billion. Where are we at? We have 14,000 applications. It's going to let that number settle for a second. Right? We build all our applications pretty much. Right? We have applications that are actually many years old. So we have a maintenance problem, and we actually have a scale problem and a complexity problem, not caused necessarily by the problem, but by the fact that we've been solving it for a long time. We have millions of lines of code. One of the things we do every night, we take all of our Java code and we recompile it and we send to all the developers of Java, these things that you've done in your code are not terribly good. We'd rather like you to fix them. These things, if you keep them in your code, it isn't going into production, right? So we've taken a section of the code and we're trying to improve it. I just use that as an aside, right? But there are things we're doing to try and get our arms around the complexities. We have just under 1 million square foot of race floor space in data centers. By the way, we've got lots of things we call machine rooms, which are in offices which are not classed as data centers. So data centers are big things, right? They have generators, they have UPS, right? I never dreamed when I was coming into finance that I would learn about how we build things, how we power things, what a static transfer switch is. Still not sure I'm happy I know what a static transfer switch is, but I've actually seen one that's blown up, right? So you come across all sorts of interesting things in the world. I'm going to hurry up because Stephen's much more interesting than I am. But we have scale. We've got 150 petabytes of storage. And it grows 40% a year. That's very scary. We actually have to make sure that we retain and guard private information. We have many pieces of information about people's social security numbers, account details. Those things have to be guaranteed that they do not leak out into the public domain. So we care about security enormously. We've got 1.4 million network ports. All the other numbers you can read. We've got 35,000 BlackBerries. We are going mobile. We've got 300,000 desktops. We're actually using VDI, so we can log in from anywhere, which is very cool. Except I was explaining to Stephen, my laptop has nothing on it, so if I lose it, it doesn't matter. But it also means if I don't have a network, I can't get to the presentation, so we couldn't have put it up here. Luckily, Stephen's not yet on VDI, so he has the stuff, so we're in good shape, right? But we're evolving this all the time. So that's our scale. And whilst it's not on this slide, the number of dollars we spend on infrastructure is approaching $4 billion a year, which is quite significant. Right? So we do technology in a big way, but we do it to support the business, not just because we like technology. Today, we think and realize that the challenges are scale and complexity. There are a couple about how the problems get resolved, but scale and complexity are the big things. But just to show you how technology has changed our business, over the last 30 years, our profitability has gone up by a factor of 30, but we've only got twice as many people, which means that our productivity has increased massively, and we've done that through the use of technology. So at the start, I joined financial services 20 years ago, when everybody had a technology department, but nobody knew why. And we actually introduced, oh yeah, we got to have, the first computer at Goldman Sachs was actually bought, I used to be there, I'm now at JP Morgan, the first computer at Goldman Sachs was bought when the then head of the firm talked to the head of IBM, who said, you should buy one of these. And it turned up and nobody knew what to do with it. Right? But we started using computers in a big way around the 90s. Right? And we started taking applications. They were living on the desktop or on the computer, and the application drove the environment. Then we started seeing email being used, we started seeing other common applications being used, and the environment drove what we put on people's desks, and the applications were subservient to that. And as we moved further down the path, and now we're getting to a point where we're building specific environments for applications, and that's one of the things we're going to talk about today. But technology is absolutely critical to what we do. We cannot do what we do without it. Just a couple of challenges, and then I'm actually going to hand over to Stephen. But these are things that we think about. So credit cards, right? You go into a store, you swipe your credit card, and it gets authorized. In that time, we have to work out whether or not we should authorize it, right? It isn't just checking the balance, right? We're actually looking for fraud. Very interesting problem. Right? Think about how you would validate whether or not somebody's credit card should be used and approved. Right? We were chatting over dinner the other night, and it was fairly obvious that if somebody swiped a card in New Jersey and then 10 minutes later tried to pay for dinner in San Francisco, it's probably not the same guy. Right? So these things are important to think about. And processing that is important, but we don't have infinite time, so we've got to do it quickly. Because actually, if it took 2 minutes to authorize your credit card sales, you'd move to another company. Right? So you have to think about what that is and understand how it changes. And now talking about mobile, right? So the next challenge is, how do you move from a piece of plastic with a little magnetic stripe to actually taking what is going to be your ubiquitous device and using that to pay for what you want? What happens when you lose it? How do you ensure it's secure? How can you ensure that, we do the same level of checking in a way which you guys are, and getting people to change how they use credit cards, right? We go through the whole range of population, from young kids to not so young kids, right? And sometimes introducing people to new technology is somewhat difficult. So you have to think about those things. What have we got? ATMs. I don't know if you guys have sort of started using the new ATMs where you can just feed money into it and it counts it for you and all that. It's pretty cool, right? It does imaging, it does all sorts of stuff. It actually reads. How do you trust it? Because it tells you what it's done, right? Right. So I feed checks into this thing, and I always print an image because I don't trust it. And it's very rarely, right? Sometimes, in fact, amusingly enough, I fed in my JP Morgan, what do we get? Shares. No. See, I've lost a word now. Dividends, thank you. I fed in my dividend check, and the ATM couldn't read it, which I thought was somewhat ironic, but never mind. But there are safeguards, and you've got to think about that, right? But the things that we're now doing with ATMs are pretty cool. And you'll have either used or seen the advert for using your iPhone to take an image of the check and depositing that way. It's pretty cool. It's really critical when you think about small businesses because cash flow is so important. right? So all these advances which are enabled by technology are pretty good. You can now get your accounts online. You can get your statements online. You can get your checks online. It's all technology. And that's in the, right, the dull retail area, right? You come into the investment bank, right? So the point is we have challenges which can be addressed by technology in all of our businesses. We can talk about high frequency trading if you like. That's kind of an interesting space, but we'll leave that to after Stephen's discussed things. We have data challenges all over the place. Right? We have a lot of data, and being able to deal with that in a sensible way is actually a challenge that still we haven't solved. Right? So there's lots of really interesting things to do, and we actually can afford to do them. We just need the right people, and we need the right enthusiasm and curiosity in order to want to find the solution. And you've actually got to want to know what the business is in order to provide that solution. And one of the things which I've been very privileged to do, because I came through the investment bank and I'm now in the core technology team which looks at all of our businesses, is I now recognize that there are challenges in every one of our businesses which are complex enough to keep people busy for a lifetime. So I hope I've given you a flavor of the scale and the complexities of technology in finance. We're recognized as being valuable by the businesses. And what we'd like to do now is to move on to a specific study of where technology, business, and really smart people came together to come up with a solution. Stephen, thank you.
Thank you. Good afternoon. My name is Stephen Weston. I work in the London part of JP Morgan in the investment bank in the what used to be the quant group, but we've spun off a little bit into a smaller group whose function in life really is to look at making our applications and particularly our algorithms and models run a lot more quickly for reasons that Peter described, but for reasons that I'll get into a few more details of just from the sort of initial point of view. Back in 2008, when I first moved to JP Morgan, and I came from Deutsche Bank and a bunch of other banks, but back in 2008 when I arrived more or less at the worst point in the credit crisis. And that was an interesting time to arrive because there were a lot of problems. There were a lot of problems, and anytime you have a lot of problems, that always presents a lot of potential for solutions and a lot of ideas. And one of the first challenges that I was given by the guy I started working for, who was head of credit trading at that time, was to say, he said to me, look, it's taking us, at the very start, it was taking them 12 hours to run their risk overnight on many, many hundreds, thousands of cores. And if things didn't go right, there wasn't any time for rerunning that. And it's a bit like driving your car down the freeway at 90 miles an hour, looking in the rear vision mirror. It could be fun, but ultimately has a high probability of being a destructive activity. So we were charged with, at that point, my group was charged with coming up with a way of making things run far more quickly. And why was that? Well, not just because we wanted to run our risk and P&L calculations more times overnight, it's because we actually wanted to add extra capacity. So we wanted to take what we had and augment it, give us more possibility for doing more calculations so that we could do more investigation. And how were we going to do that? Well, we looked at a variety of possible ways of doing it. And just to give you a little bit of background, before I joined JP Morgan, I had worked with a guy who was a registered sadist because he liked to give you things that were really unpleasant to do. And I happened to have a conversation with him one day, and he said, I've got these things called FPGAs. They're really cool, and they can make things run really quickly. I said, oh, that's interesting. And he said, oh, what you've got to do is you've got to buy one of these things, you've got to learn how to program it, and I can help you. And over a period of 6 months, he taught me how to program these things from first principles in VHDL. And I realized that A, I wasn't a very good programmer, B, that the programming these things was really hard and unpleasant, C, that even if you could get them to work, convincing other people that they were going to be viable at scale was just like pushing a large ball bearing up on a slippery slope on a windy day. And so I had this in the back of my mind when my new boss at JP Morgan, head of trading, said to me, are there any other possibilities out there? And one of the things I suggested to him was perhaps trying FPGAs. And inside the organization at that time, there were all sorts of other groups suggesting other things, GPUs and multi-core and blah, blah, blah. Anyway, what we tried to do was considered very much a super fringe activity. And when I was casting around for a good partner to work with, people actually really understood how to make this technology work and how to convert it into things that would work at scale in an organization reliably and support what was developed with it. We came across, fortunately, Oscar and his team at Maxella. And that kind of started the discussion, if you like. And so really what I want to preface here is this is a snapshot of where we are now in a project that's been going on for close on 3 years. And I guess I want to stress a number of things before I go into the details, which are all interesting, but just to put it in context. It's collaborative, okay? We did not have the answers, but we knew we had a good problem, and a really, really good problem. Our credit book is probably the largest on the street, defined largest on the street. It's many hundreds of thousands of trades, of which most of those trades calculate like that. There's just like no time in them at all. Single name credit default swaps are very quick to calculate both value and risk on. But we've also got an inner core of a much smaller number of trades in the thousands of bespoke tranches, CDOs for want of a better word. And then we have an even smaller portfolio of CDO squareds, tranches on tranches, which are considered the sort of the instruments of mass destruction by various people. Anyway, doing something with them is a challenge. You can't just walk away from these things. We had them, we had a portfolio of them. We had to come up with a way of calculating risk quickly, reliably, and accurately. So it was no good being able to run the numbers like an express train. It was no good and not be accurate. And at the other end of the scale, it was no good being super accurate and taking a long time to run them. We had to be able to do both. We had to get scale, accuracy, reliability, and deliver that into a production environment. And so I think what I'm going to talk about now is probably, we believe, that we're one of the furthest ahead in the industry in doing this at scale. But I'd like to stress the very collaborative nature of what we've been doing. We had an idea internally, but we had to find a partner to work with that was capable of seeing our vision, working with us, understanding our problem, and helping us to turn that into reality. So this is a sort of an outgrowth of a talk that Oscar and I gave last year, I think it was, in Paris at the Global Derivatives Conference. So apologies for any slides that I've kind of begged, borrowed, stole, replicated, or shamelessly just reused. So I'll start with a pretty slide and why we actually found ourselves where we're at. And for those of you on computer architecture, I apologize wholeheartedly here. But the basic problem, as I'm sure you're aware, is that on the standard core, multi-core machine, the actual part of the chip that's actually devoted to doing floating point arithmetic, which is what we're really interested in, is actually relatively tiny. It may run at a very high speed, but there's a lot of waiting around and there's not an ability to pipeline the instructions. And so what we're looking for is something a technology that will provide us with the ability to deeply pipeline, massively deeply pipeline our instructions to get the throughput that we needed and to convert from a standard computing methodology into a streaming computing methodology. So FPGA 101. Again, I'm not attempting to teach my grandmother to suck eggs here. I guess the most important thing that for us really, as Peter has alluded to, is that we've got a lot of computers in a lot of data centers. So one of the really important things for us is power consumption. Our data centers never run out of space. I mean, they never run out of space, but they do run out of power. And power to not only to run the machines, but to cool the machines. And typically, we needed, therefore, a solution that was going to be fast, efficient, reliable, and less power hungry. And if you like, one of the concepts that we kind of came up with, or courtesy of Oscar and his guys, was power per cubic meter, of consumption of power per cubic meter per calculation performed per clock cycle. So whichever way you want to stew the numbers, what was important to us was the ability to do a lot more calculations additively to our existing capacity in a reliable and rapid way. So what does it really mean to pipeline these things? And I hope you can see that. Very simply, moving from a very simple calculation, what we're looking to bring in here is fine-grained parallelism. So the ability to break down our calculations into very, very simple components and build very deep pipelines that will then enable us to execute those calculations very, very quickly. So typically, we were looking at moving from a standard way of doing our calculations where you would run the compiler and it builds a series of instructions that wait for things to happen and they all sync up, running at a nice fast clock rate. We're running, on an FPGA, we're running at a slower clock rate. So how are we ever going to compete? As Oscar's said on many occasions, it's impossible. It just can't be done. So that's an attractive challenge. Not only were we looking at a business problem that was complicated, but we're looking at a compute problem which allegedly just can't be done. So it was an interesting challenge to take on. So we're looking for things that can be pipelined, that can be replicated, and what we've ended up with, if you like, is an architecture which has literally hundreds of pipelines per chip, and at each and every clock cycle, and we're turning out finished values. We're actually getting values back each clock cycle, rather than waiting for numbers of clock cycles to deliver values in the Intel world. Does it work for everything? Well, here's one study that's influenced us fairly heavily when we started. And this is, as you can see, it's a paper written in 2008, which kind of describes GPUs versus FPGAs, because this is one of those things that, as I'm sure you can appreciate, turns into a bit of a political kind of, if not a religious war. On the one hand, you have in the blue corner, you have the GPU guys, and on the other hand, you have the kind of FPGA guys, and somewhere in the middle, you have a lot of blood on the floor. And what we found was, yeah, pretty much in organizational terms, there was a lot of blood on the floor. The FPGA guy, the GPU guys, claim that, of course, anything you do with FPGA, you can do with GPU, and you can do it better and faster. And so, what did we do? We bought a GPU, and we sat down and we programmed a GPU. And what did we do? We took our model and we got it to run about 14 to 15 times faster on a good day, pure end-to-end. And so we thought, well, okay, that's not bad. Now let's have a go with FPGAs. And when I told my boss how long it was going to take, and he said, well, how long is it going to take? Oh, it'll take me about 6 months. And he said, oh, no, that's no good. And we therefore went to Oscar and his team, and Oscar said, okay, well, for a fixed price, given a period of time, we can do this. So we did a proof of concept. And really, the proof of concept underlined the fact that here, FPGAs do very well on things that are complicated, have a lot of low-level hardware control, and can be pipelined in a very deep way. So what did we end up doing? Well, our initial project was a proof of concept, and that enabled us to run a small portfolio, representative portfolio. And here we used a bit of graph theory to represent our entire portfolio in a much smaller series of representative transactions. We reduced our global portfolio down to about 450 trades that we thought gave a reasonable representation of the value of the book, not the risk in the book, but just the value of the book, to see if we could accelerate value first. And that was done with a given an initial design of a node, and based on the result that we got, we ran about 30 times faster as had been designed in the first place. Based on that, we then worked with the Maxella guys and built a 10-node box. And each of the nodes has 2 FPGAs, a bunch of memory, an Intel 8-way CPU, all linked together by a nice high-speed backbone. And we put our bit portfolio on that, and then we put the whole portfolio on this time, not just our representative series of trades, all the several hundred thousands of trades. And we cranked up the handle, and we got, with a lot of effort and a lot of single-minded stupidity, determination, and just sheer guts, and a lot of late nights, we managed to get the book to run at about 130 times faster, at which point we knew that we were onto a good solution. So we went back and we actually built, in terms of the comments that you're probably interested in, a 40-node computer, which is basically pretty much a supercomputer at that stage. And the design you can see there, it shows you kind of what we put in. And for those of you who are heavily into this kind of stuff, and again, I bow to the superior brains amongst us. This stuff was more interesting to me from the point of view of how much could we push through this machine. Because our biggest problem is the ability to push a lot of data through very quickly and get a lot of answers out back the other way. So it's a problem of balance. Streaming the data through the computer at the right rate. How fast can we push in trades? How fast can we pull out our results? Because as we push the volume of trades in, the volume of information results that comes out at the other end is typically 10 to 100 times bigger. And for big scenarios, it's about 1,000 to 1,500 times bigger. So streaming the data in was a really, really important thing to be able to do. And here's an explanation, really, of how this hangs together. So we started out with FPGAs, and from the FPGAs, we actually took our model to pieces, and we built a series of kernels. And the kernels worked together to describe our model. How does that actually work? Well, our models, the model that we started with was a credit derivatives model, and it was composed of 3 basic elements. The first element is a copula to find out the marginal distributions. The second component is a convolution to find out the area under the curve, if you like, and that effectively then generates for us a single default curve which represents the cumulative default structure of that entire tranche. And so we end up with a series of kernels which represent the original C++ code and a manager kernel which runs the whole thing for us. And our code starts out in C++ and ends in C++, and we built an API over the top of that to do the distribution. So now we have effectively a stack which delivers what we need. We have speed under the bonnet in raw calculation terms. We return to our original library, which is written in C++, and we have an API that also delivers distribution in a very bespoke kind of way. Because the original way we started using Symfony and a general compute model just didn't deliver the speed. We could get speed at a point, but then we lost a lot on distribution. We lost a lot on throughput. So the design here was very much designed to take account of the structure of our problem. More memory to allow us to stream the data in and out, a kernel design which allowed deep pipelining, and coupled with a specialist OS designed by the Maxella guys to enable us to talk to the chips in a very efficient way. So compute architecture, as you can see there, our core libraries here, called Triton and QLib, those are what we started out written in-house. Manager kernel interaction at the detailed level. Again, what are we really interested in? Well, static versus dynamic control structures. We have a lot of points in our code where we are doing highly repetitive calculations, FFTs. All of these things can be optimized, and typically, you know, I'm sure that you can find good FFTs and bad FFTs, some that work well in hardware, some that work well in software. So it was an exercise in not only changing our underlying code, but also modifying our algorithms. What we also went through and found very useful was the iterative nature of the acceleration process. Again, this for us was a very, very useful exercise to understand our source code in a lot more detail than we'd ever gone through before. The sort of deep nature of analyzing the structure of our code. Where was our code really spending the time? How much was being spent in execution? How much was being spent in waiting? How much was being spent in moving data around? So we had to spend a lot of time analyzing our problem. And again, we can see analysis, transformation of the code, partitioning of the code, and then implementation. And typically, that process takes about, we've discovered now from the process we've been going through, it takes about 3 months from starting with a piece of C++ code to ending with a version of that code that now works on the FPGA and matches the price of one trade from start to finish. So it's becoming a process for us that's both sustainable from a development point of view and maintainable from a business point of view. Again, I guess the thing that's really important to us as well is the tools that we've had to work with Maxella to understand. And in particular, one of the things that we found very useful is being able to predict up front with a high degree of accuracy how fast we're going to be able to make our code run in an accelerated state. it's all very well starting out saying, how much do you want to accelerate? Well, it's a bit like saying, how long is a piece of string? What was the target? Running as fast as possible is obviously what we were after, but what could we actually expect when we started out? We needed some kind of concrete target to be able to say, this is what we're aiming at and this is what we expect to achieve. And the Max Parton tool that these guys developed enables us to have some concrete idea before we start out what we're likely to end up with. Again, a lot of this is highly process driven, and again, we're really interested in control flow through the program. A very useful insight for us was working with these loop graphs, if you like, I'll call them loop graphs, to actually see where the control flow of a program works and to see where the hotspots are in data throughput, in execution. And these, although they look very simple, it's not the way you would normally analyze a piece of code. And so for us, there was a lot of insight to be gained from understanding where we were spending a lot of time moving data, where we were spending a lot of time calculating, where we were spending a lot of time returning data. So again, iterative, I guess the overall speed up then, again, nothing, I'm not trying to hammer home the point other than to say that we were very interested in how much we could speed up our code by combining memory and tools together. But really, what did our model look like? What's the detail here? Okay, so effectively a standard Gaussian copula model with stochastic recovery. For those of you that like the detail, it's the Hittier version using inputs as base correlations. So effectively, we take base correlations as reversed out of index tranches in the market from which we produce a series of effectively a correlation cube, which gives us the input to price the bespoke tranches. So this was our original code after removing the C++ class hierarchy, and this was really very interesting for us. We started out with a big chunk of C++, and after we threw away all of the stuff that wasn't really doing useful computation, but I'm sure was very nice for people who like the sort of the purity of the subject, down to actually pure C, so double in, double out. That's really what we were after, because a lot of the other stuff is really not helping us speed up the code, and it's not helping us actually in the understanding of our code. And I'll come into another example in a little while, how that just gives you a nature of how much the problem affects us. But here's a view of our C++ after we've removed the C++ features, if you like. One of the things that we found in our code, and Oscar I'm sure would attest to it, is massive use of templates. They're like a disease. With just templates, they come in, they spread like the worst possible virus. And not only templates, I mean objects. I mean, why do we have to have so many objects in our code? And we came, very interesting from our point of view, we came to the conclusion that quants like objects because they're a convenient way to think about things, which is fair. I mean, data can be put into an object form. It gives you abstraction. But as was pointed out to us on numerous occasions when we were trying to speed things up, abstraction effectively kills parallelism. So it's very convenient and it's very nice and enables the quants to sit there and do pure type things and have pure thoughts, but it doesn't give you fast code and it doesn't give you fast computation. So having run our analysis to find out where we were spending our time, we can see pretty much extensively that we end up in the copula, the convolution, and updating our accumulated loss distribution. So again, no great surprises to us as a bunch of quants. We pretty much knew that's where things were spending their time, but what we didn't really know was when they were in there, what they were doing, and how much information could be reused, how much could be pipelined, how much could be thrown away, where we could reorder the calculations, how we could rebalance the algorithms. And here's just a slight summarization of how our convolution works. And effectively, you can think of if you like, the detail that is really not so important here is understanding the fact that we unroll the program. So we go from computing in time, effectively, to computing in space. And that's the main thing that took us a lot of time to get our heads round as a bunch of quants. There's a bunch of quants, we tend to think in kind of linear time. You know, we start here, we end here, a trade starts here, a trade dies here. We think in linear time. So trying to unroll our algorithm into the spatial domain was quite a struggle for us to start with. And so that for us, if you like, is quite a breakthrough as an understanding. And then putting it all together, using the CPUs to drive the FPGAs and to push the data through in a streaming computer model. And if you like, here's a nice way of looking at, here was our flattened C code minus all of the undesirable features of C++ that we didn't really need, down to the Max Compiler Java code. I just realized I've got a slight glitch in the middle there. Sorry?
I thought I fixed it.
Yeah, so did I, but there we are. But you can see, I won't go through the detail line by line of the code, but you can see there's a very good correspondence from the original C code through to the Max Compiler Java code, all built in Eclipse, I would add.
So most of your arrays are one-dimensional, and your mix of data types is relatively simple?
Yeah, our mix of data types is relatively simple. Pretty much all our inputs are doubles.
Doubles?
Pretty much starting, well, that's how they start life. Whether or not we actually need them as doubles is another issue. And that's another, if you like, that's somewhere else that we found that, you know, starting with a perceived level of accuracy, as you dig into the problem, you realize actually you don't need double arithmetic in every single place. You can make do with a lot less precision, and that gives you the speed. That gives you the possibility of having speed. And that's a very, very difficult argument to win with quants off the bat. Because in the blue corner is all the quants with an obsession about having to do double arithmetic with everything. There is no question. Everything has to be a double. But in the red corner is the sort of more practical group that says, well, hang on a minute. What really matters here is the ability to produce the value of this trade that's right to the cent when we book it in our booking system. Yeah, because we can't book to more than a cent of accuracy. So what's really important is to get the right value at the end of the day. And so you can start to see where you can save time and effort and accuracy to speed up what you're running. Does that answer your question?
And then most of your array lookups are all largely one-dimensional?
Pretty much, yes, apart from our input volatility, our input correlations, rather.
So you modify your compilers to automatically assume all data types are double, or everybody explicitly declares everything?
I would like to give you a nice easy answer to that, but there isn't one. It would be really good if our quants all had the same homogeneous approach to life, but we've got, just to add the complexity back in, we've got roughly 250 quants, and although we have coding standards, they're more kind of advisory, and they're more honoured in the breach than the kind of the practical reality. Broadly speaking, our code is actually well structured. We take a lot of time and thought about it. But rigidly trying to impose programming standards is a lot harder than you may think. Why? Well, we have hundreds of thousands of lines of code in our models, and they haven't just all arrived on one day. We've been at it for a very, very long time. And the biggest problem that we have isn't generating new models. No, far from it. Any good quant that we would employ could generate a new model. The problem is that the new model won't be the production model. And probably the delay between coming up with a model and seeing it in production at scale across a complex portfolio can be as much as 3 years by the time we've done the testing. We may have a model change that can be quick, but our models typically take somewhere between 6 months and 3 years to get into production. Depends on what they are, and once they're in production, changing them in production is a huge task, because then you've got to go through and justify why values have changed from where you started to where you are, and if it gives rise to a large P&L swing or a large risk swing which may induce rehedging, those are serious decisions that have to be taken at a fairly senior level, and the computations have to be run quickly enough to be able to get that cycle down to an acceptable level. Yes, when the market gaps, we, like other houses, have to move quickly, and we do. Excuse me, but those tend to result in changes to existing models rather than a brand new model. I mean, the last thing you do when the market changes is to throw in, here's a model that we're not quite sure, we'll throw that into the mix, maybe that will help. It's a bit like throwing a grenade into the duck pond. It's not a good idea. So really, I'd love to tell you that there was a super homogeneous way of doing these things, but in reality, each quant group will have a slightly different approach. And interestingly, within JP Morgan, a lot of our code started out in one group and morphed into another, and then went round to another group, etc. So, for example, credit grew out of the interest rate group and the equity group. And so coding standards kind of mean different things in different places.
Stephen, do you write all of your stuff in C++ or C++ and Java, a little bit of Erlang, a little bit of Clojure, a little Lisp? So
everything, all of our quant code is written in C++, and within the C++, within our quant code generally, we have to support a lot of platforms. So we typically support, obviously, Excel, because all quants and all traders inevitably want to be able to run everything in a spreadsheet. Doesn't matter what it is, they want to be able to run it in a spreadsheet, including their full risk, which obviously is a bit tricky. And then it also has to work on Linux, because that's what all our farms run on. And so we obviously have to support not only the standard Microsoft compilers, but the GCC compilers, and we have to deal with all the different versions of Linux, etc., etc. So it gets to be quite messy quite quickly. And then within our quant environment, we also support Python natively inside, so we can do a lot of quite clever stuff with Python inside. So it's mainly C++ for the pure analytical models, and then Python for a lot of facilitation inside. When we want to do, for example, if we want to build internally to our models, if we want to build the ability to bump things that we can control rather than the technology people can control for various reasons, where there's tends to be a bit of misunderstanding sometimes, shall we say, or difficulty in iteration. Let's put it like that.
And these codes actually began as C++ codes originally, is that correct?
A combination. Some of the quants like to work with MATLAB and Mathematica to start with.
Well, I'm just wondering how far back, how old
is some of our code?
Can you trace to?
Some of our code, the oldest bit of our code that I've come across is like 1979.
But the C++ I know did not exist in 1979. So
no, interestingly enough.
That was all COBOL or Fortran?
Interestingly enough. If you really want to get into the more detail, we started out with some of the stuff in C. Now we kind of added C++ functionality on top because it was perceived to be a good thing to do. And it has lots of good features, and it's very, very useful, don't get me wrong. But there's definitely an argument to suggest that we may have gone a little bit over the top in certain places. How? Well, a lot of our data structures, for example, have become very complex. We've added a lot of inheritance in, and base classes and all this kind of stuff, all of which in theory have very good usages, and all of which in theory are intrinsically good in some way. But when put into quant libraries and pushed out at volume, they don't result in fast execution. There's a lot of time spent in constructing objects and deleting objects and passing structures around and dereferencing pointers and all this kind of stuff, which once you put features in like templates, it just it just multiplies in all the dimensions you can imagine.
But I think that's actually a very good example of things which, because code ages.
Yes.
We've been running systems for many, many, many years, and you tend never to start with a blank sheet of paper.
Absolutely.
So as coding practices evolve, as we learn things, we don't necessarily go back and fix what we've started with, right? Because we're a commercial organization, and you actually want to get value from the return, right? So we invest where we need to invest, and if something's working okay, it's working okay.
Well, yeah, I'm familiar with millions of lines of Fortran for reaching Neptune, for instance, and how a 4-bit word, difference between a 32-bit machine and a 36-bit machine, which of course represents a 72-bit double, or maybe a 128-bit double if you're working on a Cray. Because you guys probably may have had Cray architectures as well too, and they have their little quirks, their floating point, and other things. Well, too. I mean, there's a big, long, vast thing. But also, how you invoke a compiler, it has serious performance repercussions as well too. So the Cray people in C said, "No, we're just going to ignore doubles. We're going to say doubles and singles are the same thing." And 64-bit entities as an example, but you know, if you're in a community that you're assuming you're looking for a 128-bit C as an example, whereas a double in Fortran represents 128 bits, and like.
Well, to answer your question specifically, one of the problems that we have is perhaps slightly different to other areas, where we will observe interest rates and exchange rates, for example. Let's take an interest rate, which is typically saved to 6 decimal places, or an exchange rate, which is typically saved to 4. Or we create a probability, a default probability, or a survival probability, which is now between 0 and 1, and will have lots of digits. Then, when we've calculated the value of a unit dollar of a trade, for example, we then multiply it by, and it's not uncommon to, billion-dollar notionals. Okay, so now you really have a problem that if you lose accuracy over here and you're multiplying it by a billion, pretty quickly you're out by $10,000 or whatever the hell, and that's not an acceptable level of accuracy. And that's what really creates the problem. You have to figure out where you require accuracy, how much you need to be accurate in one particular place to make sure that by the time you get to the end, you have the degree of accuracy that you require in your books and records. Because it's a strange but true fact that when we make changes to models and to algorithms, the first thing people want to have explained to them is, why is this value now different? And can you explain, every single way? Let's say the value is changed by $10,000. It's been accounted for by 3,000 here, 2,000 here, 4,000 here, and 1,000 here. Okay, now we can move on. But we have to explain it at that level of accuracy. And the problem for us really is billion-dollar notionals times very, very small fractions on the other side. Okay, so again, moving back to the code design, and here you can see from a structural point of view where we ended up with a number of kernels, again, identifying the convolution, the copula, the FFT, and you can see the structure that we built up. And I guess one of the most interesting points from our point of view at this stage is that we discovered that you could have different bit streams for different levels of accuracy and therefore different speeds. So for example, when we're doing a simulation, we don't really care when we're looking at whether or not the value of a multi-billion-dollar book, we don't care whether or not the trade values are accurate to the cent, being accurate to nearest $10 when we're doing a simulation. Has the value of the book changed by 1 million or 500 million in this scenario? So being able to dial up, if you like, and build with a given degree of accuracy and therefore get even greater speed for certain types of tasks turns out to be very important for us. And again, we end up for risk. Risk is another interesting aspect of what we do. A lot of our risk has to be done by finite difference. So it's bump and run. And so now you do first derivative by bump and run. Okay, so you need a particular level of precision for that. Now to do your second derivative, you're now talking about a tiny change on a tiny change. And so then to get that, you need to go back in the accuracy stakes. And it's interesting to note that some of our second derivatives, we could only run once a week at one point. They just took an inordinately long period of time to run on the existing architecture. So we needed an architecture that would give us the ability to run things fast and flexibly. And changing the models is another interesting point to your question earlier. In the periods that we've been doing this, we've made many hundred releases to our quant libraries, many hundreds of releases to our quant libraries. And to this quant library, in particular, that's affected by what we're discussing here, we've made over 150 releases in the 2-year period that we've been concentrating on this piece of work. And in fact, it only gave rise to 2 changes in the bitstream. Because why? Well, we only apply this kind of technology to relatively mature algorithms. What we don't do is write a piece of code for a new model today and immediately turn around and say, right, we've got to have a new bitstream for that tomorrow. That's not what we do. We're talking about applying this to relatively mature, if not incredibly mature, algorithms that are in production at volume and make a difference to our ability to calculate our risk. Clearly, at some point, algorithms become stable, and that's when we would think about migrating them into this technology. And I'll touch on that in a little while.
Yeah, it's not so much the algorithms. What's curious to me, in both looking at the space and nuclear and cryptologic codes, is the fact that the surrounding environment tends to also have to be carefully modified for both performance as well as correctness. And I mean, we have similar kinds of things both with precision and performance. But again, it's that you can take a performance hit where you least expect it simply because of typing assumptions. And I've learned when I look at a chunk of code, I also have to think about what the data structure above it, as an example, are doing. The fact that you're doing largely one-dimensional data structures, that's common to things like orbit determinations of that. But on the other hand, the nuclear guys, we do finite difference a lot as well too. For fluid flow, we're doing 2-, 3-dimensional kinds of codes, as an example. And what's valid in one set may not necessarily be valid in another.
True.
For us,
I'll come on touch more briefly at the end on different types of model that we've also had some success with doing this in a moment. Right, so structure. Again, just an example of, again, where we're looking at thinking about changing algorithms and algorithms that we started out with for doing various things, and how the number of multiplications and additions obviously makes a huge difference in what you choose. And it is a sad but inevitable fact that a lot of models tend to have something of a relationship between numerical recipes in C and where they started from. Why? Well, numerical recipes in C is taken to be trusted code, and lots of people like to start with it. And it has a habit of kind of working its way in. Before you know where you are, it's kind of in production, and then people only go back to it after the event. And I think one of the points that we've learned from this exercise is that really quants don't like doing their housekeeping. They don't like kind of tidying up the code, improving it, polishing it, making it run quickly. The thing that quants enjoy doing most is solving hard problems. Give them a mathematical problem, they absolutely love it. Oh yeah, they're down in the algorithm, they're up on the whiteboard, we've covered the whiteboard with equations, and we're off to the races. But this kind of stuff is not really considered very sexy, but at an institutional level, it has hard impact. It has dollar impact. We're chewing up data center space, which chews up electricity, which is being chewed up by space as well. If we can compress the space and the time and the energy required to do these calculations, then it has hard business value for us. It gives us ultimately a competitive edge. The ability to run our risk more frequently and extract more value from our book by understanding our books more fully is a real commercial advantage for us.
So which one did you choose here?
That'll be telling.
I'll tell you. Martin, I suspect they use actually all of them.
Yeah.
In circumstances.
It will be telling.
Yeah.
So code efficiency. I mean, again, this is just trying to hammer home the point about with the depth of the pipelines that Oscar and his team construct for us, working with us. It means that the depths of the pipelines are incredibly deep. A lot of things are going on. The calculations have been broken down to a very, very low level in order to be super pipelined and made ultra parallel. So we can do a huge volume of calculations more than we can in the traditional CPU environment. Going through the stages then of building the managers to actually link them all together. I'm not going to stand here and go through code because I think you've got the slides are available, and for those of you that wish to, you can spend the time looking at the code and looking at the examples. And if you've got any questions at the end, I'm happy to give you my email address and we can kind of talk about them offline. So I won't go through the individual slides because I don't think there's a lot of benefit to be gained from actually discussing each line of code here. We could spend a week probably doing most of that. But building the kernels, again, building the FFT kernel, I'm sure most of you have gone through FFTs ad nauseam. Just to show you what we're doing in our environment though, just to highlight and drive home the way it works. And I guess I'm kind of skipping through because the bits I really want to talk about are, if you like, building the hardware. And this is the interesting bit, was now actually balancing lots of numbers, which are always good. Quite like lots of numbers. So what's interesting now is balancing out the construction of the Bitstreams at the end. Balancing the lookup tables, the flip-flops, the block RAMs, and the DSPs or multipliers. So now it becomes an exercise in optimization. How many of these does each design use? Once you built a design, how well will it fit on the chip? How quickly can it be built? How quickly can it be modified? How quickly can it be used? All these things, which are deeply theoretical problems and very difficult to solve, are problems that had to be solved and made production worthy, if you like, and usable in a commercial environment. And lots of these problems, I have no doubt, have been solved in sort of seminars and labs and PhD theses, Oscar will tell you for one. But actually putting them into a production environment at scale in the largest credit book on the street is quite an achievement to get this far. And I guess the thing I'd like to stress is that it's been a team effort. And for us in JP Morgan, that's really been the insight, that you actually need to go and find very bright people to work with on complex problems. And here's an example of a really, really complex problem for us that we've tried to deal with. This optimization here is not a trivial optimization. It's not something you can sit down, bang into Excel, pull up the solver and say, thank you very much. It isn't going to work that way. This is a complex problem to deal with. And balancing out the resource usage on here for the copula, for the convolution, etc., that requires a lot of design and a lot of thought. This is a complex problem that, working with other people, we've actually been able to harness this for our business. Handling errors, again, so you do all this and you get an error. How do you handle the error? Again, that's a key problem for us. In our standard C++ code, we have a habit of just throwing up errors with incredibly unhelpful strings attached. Just gives you some line reference and it says, what on earth does that mean? And you get a mail from people saying, I've got this error, error 38612, out of this, in this, on that. You've got no idea where it came from. So having useful error messages within this operational environment makes a huge difference to us. Excuse me. So again, really wanting to just stress at the end of the day here, we are following standards here, the IEEE 754 standard. We're not doing this as a theoretical exercise or as an exercise in wanting to show whether or not this will work. This had to be done to very, very strict standards to deliver something onto a trading floor to trade billions of dollars on. So accuracy was obviously important to us. So again, how accurate do we need to be? That's a question really that we thought originally we just had to be very accurate. But now we've come to understand that the question is meaningless. It's how accurate do you need to be in how much time? How much time have you got and how accurate can you be in that time that's available? That's really the important question. And testing, again, testing is actually really rather interesting for us. Way more time is spent on testing than almost any other aspect of the exercise. So trying to deliver this into production, we had to test every single trade. Every single trade had to be validated and nailed down to the cent before we could even think about going into production. And what's more, we had to deliver it in a way that people could, the traders in particular, had confidence that they were going to be able to get accurate numbers and they were going to be able to get them every single day. Building something, an environment that will actually deliver those numbers accurately and reliably is actually incredibly difficult. We have a very high, and Peter will tell you, we have no worse than anywhere else, but we do have a relatively high rate of DOA on hardware. In the period that we've been using the FPGA boxes that we have now, we've had 0 failures. That's pretty impressive. Debugging, again, you can attach watches, so there are full debugging facilities. Bugs can be dug out. We can recall that, because they're statically scheduled, there's no need for dynamic debugging in this particular instance. We can have output debug files, and we can dig around and find out where things are coming from. Code validation, again, we're in a position where we have to not only confirm that we've matched our original C++ to FPGA, our FPGA to Proteus, which is our RISC system, and our Proteus existing RISC system to the actual precise valuations. So we have to do a lot of three-way testing. And when you've got 500,000 trades in this particular instance, or thereabouts to test, that's a lot of numbers to test and a lot of test cycles to go through. So in terms of that, where do we actually get to? So when we started out, we were taking out many hours, 8 hours to do a complete RISC run, and about an hour or so to run a present value on our entire book. And as you can see now, we can reduce that. We've reduced that to about 238 seconds with an FPGA time of about 12 seconds, which to us is a huge thing. Being able to actually run the book in 12 seconds end to end and get a value for our multi-billion-dollar book within 12 seconds has a huge commercial advantage for us.
Can't even get coffee.
Sorry? No, you can't even get
Don't
coffee.
even have time to get coffee.
No, we also find that not only do we not have time to get coffee, the traders were in some cases they would be running one job, but before they got, they'd be looking at the answer for one job and have another job stacked up behind to see what was coming back. So it does make a huge impact on our business. I guess the other insight that came that we discovered was that as we started to run the scenarios in particular, you can see here that we actually pushed the FPGA utilization up and a number of scenarios. So we started running more and more scenarios. Why are we running more and more scenarios? Well, particularly we're very sensitive to defaults, obviously. Our business is all about hedging the spread risk and the default risk. We can't hedge both at the same time because one is kind of the analog of the other. And so we need to run a lot of scenarios to find out. For example, the Irish bank problem, the Portuguese bank problem, the Spanish bank problem, the Greek bank problem. What we had to do was to take our exposure to all those names and run them combinatorially. So let's say we had 15 names, we had to run 2 to the 15 scenarios. And we found that, which is a fair number of PV scenarios. When we first started out, that wouldn't have even been thinkable. Now we can actually run this stuff. Yes, it still takes a couple of hours to run, but we can actually get the answers back. And that ability to identify the speed, use speed to identify problems and then try and deal with those problems in advance. You can see, as we started to run more scenarios, there turns out to be a bit of a sweet spot that if we run more than about 50, the FPGA compute time doesn't improve anymore. And if you make the number that you run in one batch too big, actually it starts to go up again. So there's a limit to how fast you can stream the information in and out.
Did you notice any difference among countries?
Again, you can't tell me.
Yeah. We obviously have a very big book, and therefore we probably have the biggest exposure to most of these things around, but not to everything by any means. What we did find, though, which is the most useful thing for us as an exercise, that where we thought the risk in the book was more or less in where we thought it was, but it had a different character to it. We found that we had a particularly interesting sensitivity to the ordering of our defaults, which we've never been able to explore before, because actually running orders of defaults, so this name, then this name, this name, then this name, then this name, etc. I mean, you can work it out for yourself.
Did you suspect that ordering could matter?
We knew ordering would matter, and in fact, what actually turns out to be a problem is the combination of ordering and dispersion. So having in any portfolio a spread of reasonably tightly clustered names with 3 or 4 names that are extremely widespread names and therefore much more likely to default. It turns out that as correlation structures compress, as markets become more volatile, correlations become much more closely clustered, and that changes the effect of dispersion and then feeds back onto default. So it causes a lot of problems for us because we can't hedge both spread and default risk at the same time. So it gives us the insight, if you like. It's not the answer to everything, but it gives us the ability to look at things that we couldn't look at before. And that's extremely valuable to us. So a postscript, I think it was Victor Khayyam that said, we liked it so much we bought part of the company. I think he bought all the company. But
When did you decide on 20%?
a bunch of reasons. But it illustrates the fact that there is real value in this technology to us as a company. And we've also now subsequently applied this to other asset classes. And so to answer the question that was asked earlier, we have not only applied this to particular kind of modeling in credit, we've also built working with Oscar and his team, we've also built a multivariate Monte Carlo model, which we've managed to run even faster, about twice as fast as we've run the credit, about 260, 280 times faster. And we're also just completing a migration of a model for a tree-based model for long-dated FX trades, where we have a particularly large portfolio also. We're looking at pushing this into high-frequency trading as well, and that's likely to go live in the fairly near future. But you can see, from our point of view, it's taken us a while to get there. It's taken us about 3 years, and it was kind of slow to get started, and then it started to accelerate towards the end. But there is definitely a critical point that you need to pass, where you need to sort of, if you like, do battle with the forces of light and dark, because that's how these things tend to be characterized, unfortunately, to be able to achieve something that moves you forward in the industry and gives you a step change. And this to us is a step change.
Is that why you switch to the dark side, as you say in your bio?
Well, they're more interesting problems. And I get to deal with a range of problems that I'm very lucky in what I do. So I also represent JP Morgan on various external risk committees in clearing in Europe and in the US. And you see issues arising there that will affect us and are affecting us and how we model things. I mean, particularly with the move to put credit derivatives into exchanges. Dodd-Frank, etc., has kind of said, well, this is the way we're going to go. But clearly there are issues around systemic risk. Just putting all these things in one place and saying we can now clear them, that also introduces a different type of risk, concentration risk. Putting, for example, in Japan, with the corporate relationships that you have in Japan, names of the owners of the index or members of the clearinghouse are also names in the index. And if you then cluster that risk closely together, that makes a lot of difference potentially, and that will feed back into our model development and has fed back into our model development. So it does give you crossing the Rubicon, as it were, and going to the dark side. They have chocolate there as well, which is better. So it makes it interesting. Thank you.
We have time for a few questions. And Oscar, if you want to stand up, you can identify yourself. You're sort of the elephant.
Or hide, one of the two. No tomatoes here, anyway. But small stem.
Yes. To what extent is JP Morgan's, I don't know, strategies sort of computationally limited, and how is the change of your computational infrastructure sort of shifting how you're going to do business? Or what businesses you're going to do?
Well, there's two parts of the question. We're always going to be limited. Our traders always want to do more. Our quants always want to have more complicated models. We always want to build and answer and ask more interesting questions. We actually have to face the harsh reality of the fact that we have budgets and we have timescales. And in most of what I'm talking about, well, all of what I'm talking about here is for trading. It's on the trading side of things. So that the cycle is pretty short, and the requirement to be responsive is extremely strong. So we have finite budgets. Excuse me. We can make changes. We can develop, but we do have a pretty hard budget constraint that if we're delivering value to the business, they will give us a bit more budget, clearly. But there is also a finite resource on the budgets on the business side. They're not going to give us an infinite amount of money to do these things. But as we've begun to deliver value and convince more and more of the business that this is a valuable technology for us as an institution, so we're beginning to think more broadly about it. And that will change the nature of how we look at computation and how we look at this technology in particular. When we started out, we had a relatively narrow view, like looking through a cone. We were looking sort of at a relatively targeted series of applications. We could just see, kind of more complex models. But it turns out there are obviously other places that we could use this technology, not just in risk, but as Peter said, in pattern identification, for example, for credit card fraud or processing mortgages, etc.
So the biggest constraint is actually time, right? So as Stephen said at the start, knowing what your risk is 12 hours after you need to know it is not helpful, right? Deciding that will allow you to buy what you wanted to buy 5 minutes after you asked is not going to be helpful. So our biggest constraint tends to be what can you do in the time? And what this example shows is that knowing what we wanted to do and then looking how we could optimize it to do it in a small amount of time, that was the start. And then what we did is we saw that, gee, we can do it so quickly, we can now ask a bunch more questions. So we're doing that. Now we've done that, there's a whole more question, right? So what we can do with the time that we deal with is the interesting thing, right? And whilst in some ways we should never be constrained by budget, because the budget should result in value. Right? If you have to spend $1 million to earn $1, we're not going to do that. Right? But normally it's the time period, and you can apply that to any of our businesses. Right? So settlement, we settle a lot of dollars. Right? You've got to get that done before you open the next day, because you need to know where your positions are. We provide services to many of the funds out in the market, and if we don't tell them what their position and risk is before they open in the morning, they'll go around the corner to the other guy, right? So we have a time constraint, and sometimes that time constraint is simply data management, and sometimes it's computation. So this is a great example of where we had a constraint, and we changed the constraint, and suddenly more questions can be asked. And so what's also happened is we're now saying, gee, if we can do it there, where else can we do it? How can we get time back? And so that's really the constraint which we deal with in all of our businesses.
But the speed up is not uniform across everything you try.
Oh, correct.
Some places the leverage has been...
No, this is one of many things that we're doing, right? It isn't, and you know, one of the interesting things is as we talk about this particular project, people think it's a general purpose solution, right? And it isn't, right? But we've actually, if you think about the way that technology has evolved, we migrated, and I said at the start, we've migrated from, you know, technology was brought into our business to do a specific task. So we actually used a lot of Unix workstations in the early days because we actually wanted to do valuation models which happened to be developed under the Unix operating system, and that's what we needed. Then we started seeing the introduction of Windows workstations because we actually were starting communicating with people, and we were doing Excel, and we were doing this, and that became a general purpose utility which we then force our problems into that general purpose. Now we're taking some of those problems and moving them to special purpose or bespoke, and we're seeing great value from that, but it's not general, right? So it really is, you know, choosing carefully where you apply these things. And the general solution is actually where we've not worked out what we want to specialize yet. So you're seeing chunks taken out of the computation problem. Anything else?
Have you seen changes in the market based on the fact that the information is available? Obviously, your traders are using it, but is it pervasive enough that you can actually see a difference in the way the market behaves as well?
Early to say. I mean, credit is a slightly different example because the credit markets aren't perhaps as fast moving as the spot FX market, for example. But it certainly gives our traders a capability that they didn't have before. It will take time to monetize that, undoubtedly, and to make it pervasive. And we're in the final stages now in the credit project of actually delivering this into our production architecture, so it becomes fully integrated with all our existing systems. Whether or not that proves to be the right move, or whether or not we should perhaps leave it where it is and build something new on the side, is something we will go through over the next 6 months or so. And again, we will learn from that experience because on the interest rates, on our interest rate product side, where we've applied the same technology, we've already managed to integrate it with the existing interest rate system there. And on the FX side, it's also similarly going down the same route. They have one system there which actually will deliver it into the production environment very quickly. So the problems are different in each business because of the timing and the sort of turnover and speed of trading in some of the businesses. The existing systems that we had to integrate with, which again, that's that's not a trivial problem in any large organization, but it's probably more so in the banks, in the big investment banks, where developments have been very much driven by market pressure. So here's a market, we need to be into it, let's get into it straight away, and things get dragged along, and you end up with a lot of legacy code because certainly on the quant side, interest rate bootstrapping algorithms, for example, have been around for a very long time, and the ability to bootstrap a credit curve has been around for quite a while. But those things, as you start doing them with huge volumes of trades and building them into more complex models, it changes the nature of the beast, and then the markets change as well. So, for example, because of the way the liquidity changed in during the credit crisis, a lot of banks are now moving from perhaps using the Fed funds rate to looking at the overnight index swap rates at the short end of the curve. And that changes the way in which then we will look at our hedging and the way in which we build that forward into our other models. And we've got projects going on that kind of ripple those changes through. But a lot of the effort is typically taken up in existing systems. You know, we always have a legacy of systems and models that we have to contend with. And so adding extra computational capability gives us degrees of freedom. It just gives us more elbow room and perhaps more time to think about doing other things where we would have been facing constraints elsewhere.
But more generally, technology has absolutely changed all our markets.
Yes.
Right. So this is another aspect. So.
Yes. Has program trading, actually trading using programs to trade, tens of milliseconds reaction time or less, put additional pressure on your computational monitoring and capabilities?
No, because that's a different deal.
I realize. Yes.
So program trading is actually taking big portfolios and managing those through the market. High frequency trading is where you do trades in small numbers of milliseconds and a very large number of very small movements. And so technology is certainly critical to both of those, but those tend to be lower computation cost, because what you're doing is you're actually looking at an element and a price, and you're not doing very much calculation, you're doing a decision, because you've got a very short period of time and you're trying to move things out. In terms of the classical program trading, what you're trying to do is to produce the best value possible for your client. Because if you dump, 1 million shares of, you name the company, it's going to take the price down. So you try to do that in a way which is most appropriate for the value for the client.
But in the high frequency trading now, the market can move quite dramatically in a very short period of time without any human intervention. Mm-hmm. So there's an additional risk there.
That's moved very quickly in the old days too.
Yes, right.
The recent crash was not the first flash crash.
Right. Yes.
High frequency trading.
High frequency trading is an evolving market, right? People are in there. There's companies like Jump where they're in and out in a day. They never ever take a position. They never carry anything over the close of the market, right? So they're providing a liquidity base, right? We have to be in that in order to provide a mechanism for our clients to be able to move in and out of the market, right? So there are different reasons for being in the market, right? So yes, we're in the high frequency trading market, and we have a lot of technology in that space, and indeed we're actually working with Maxillar on looking at how can we take what is essentially a short pipeline and speed that up, right? But the challenge is somewhat different, right? But we're starting to see how we can apply the tools to service that challenge.
And I guess also, just in the same vein, the ideas flow in. What's also interesting, the ideas flow through the institution. As Peter said, the work we're doing with Oscar in the equity space, the equities and the credit guys speak on the phone all the time. And I literally yesterday I had an email from our head trader on the credit side saying he's got some high frequency trading strategies he'd like to talk about, and could they use the same sort of approach. So there's a sort of a feedback mechanism going on.
So if
you're saying you can run the model now in 12 seconds. How close are you to just having a real-time image of what's going on with your portfolio? You said you're not talking high-frequency trading, you're talking larger trades that move maybe slower. Are you close to just having a model rather than a...
We could have high frequency. We could have basically continuous risk management now. That's undoubtedly true. It's pretty much there. Okay. The question though is much more about time. Just because we can compute those numbers very quickly, it doesn't necessarily mean the traders will look at them. Yeah. And what I mean is
actually why we don't use high frequency trading with people.
That's right.
Just to replace the trade.
No, because the question is different. It's more just a question.
Different.
Yeah, the question is that what you're talking about really is, should we have effectively real-time, super real-time real risk management? You know, can we compute the numbers continuously? And we could. To all intents and purposes, we could. But would it be useful? Because the traders, don't forget, it becomes a question of numbers. Let's take our credit traders. Each of the credit traders will be looking at a number of names, a number of companies that they're responsible, and a number of sectors. So they have, and you can imagine the numbers. So that each one looks at maybe somewhere between 10 and 30 names. So he's monitoring between 10 and 30 names. Now he may have something between 100 and 5,000 trades on with each of those names. If he's getting that information continuously and he's also making trades, what's it actually giving to him? What's much more interesting and more useful, rather than sort of real-time risk, is to be able to run scenarios. That's really what's valuable. So what will typically, where we're looking at moving now is that, for example, we have typical types of trading scenarios. So what will happen if the market gaps? What will happen if the short end rises and the long end falls? And what happens if the financials do this? So the ability then to run those scenarios either on demand or overnight. So when the trader comes in the morning, here's his top 10 scenarios that he might look at today, and here are the numbers for yesterday. And so he can now, it becomes a better information and trading support tool. It's a decision support tool. I think is more valuable in the credit markets. It's obviously much more likely in the spot FX markets that they're going to want real-time risk management. So you have to adapt the information requirement and the delivery to the market.
So actually the trader would really narrow down the choices on the scenarios.
Yes, absolutely. So first of all,
a real-time control story anyway, typically.
Yeah, I mean, well, typically
when we start out slow, like think of a fighter jet. Yes. They're going to actually move the missile by hand,
yeah.
Right?
I mean, when we started out, we were getting demand for, we just want to run all these scenarios. Well, you know, what are you going to do? Oh no, we don't know. We're going to look at them first. We'll find out when we've looked at them. And literally, there was we ran lots of numbers, and they spent hours poring over them. And they then decided, actually, well, this one's irrelevant, this one's irrelevant. These are the ones we want to run. And so we ended up with a much more focused set of requests and ideas. And then they sparked other ideas, and the traders talk as an information flow. And you get traders, typically, the traders in credit used to trade interest rates because that's probably where they came from, and they probably used to trade FX, and they're all on one floors above and below each other, and they talk. And so we start getting requests for different scenarios to be run across different types of products. And I think that's where the value is, more than necessarily continuous risk management. It's not necessarily all that valuable in the credit markets. It's a question of what the traders really need and want.
When you say talk, you mean there's little English going around?
Yeah, I mean literally. They're exchanging
if you want to do that from a control perspective, yes, you would have to translate that into sets of scenarios. And then at best, you might be able to select among those. And the two can say it. The two speaking partners can maybe help select down which scenarios.
I think that's right. I mean, what's also probably needs to be emphasised is that this is not the kind of capability we would put on every single trader's desk to run on demand. Sure. It's pointless.
It's on top level.
Yeah, it's top level and structural views where it becomes very useful. So the heads of trading or the heads of sectors of trading will say, well, I'd like a scenario that does this, or tells me about where I might end up with exposures if this were to happen. And we've had a lot of interaction with the heads of trading, the heads of risk, looking at particular types of scenarios. I mean, obviously for a credit business, default is the main thing that we look at. Spread, yes, but default is where we are most interested in. It's a much more discontinuous problem to deal with rather than spread risk.
Still start to sound more like in the military. That's why I brought up the missile story.
Yeah.
I mean, that kind of dynamics is starting to, with real time, started to show up in your domain, basically. They're just talking about it is too slow.
Yeah.
The missile is coming.
Yes, yes.
I think we're going to have to break it off. It's 20 minutes past our normal time. And while we have occasionally had sessions that go on for a long time, this is not industrial automatic. If you have further questions, come down and bring them up. But meanwhile, I just want to thank you. It's been a great time.
For more, please visit us at stanford.edu.